Hi all. I thought I'd do a quick run through of the first 20 questions on the 2012 AP exam. It's a pretty old exam that's been published for a long time. It's one of the few multiple choice ones that are out there for free. So I just thought I'd go over the first 20 questions very quickly in case people want to know more. So let me share my screen. Share screen. Okay, so you can find this in a lot of different places on the internet, but it's the 2012 practice exam. First question is basically, which one of these represents the greatest standard deviation? Standard deviation in general is the typical distance from the mean. And so anything that's closer to the mean is going to have a smaller standard deviation. And I think A is probably a pretty good distractor, but because I've got all these down at one end and all these down at the other end, when I actually do the calculation for standard deviation, B is going to come out the highest because these are typically much farther away from the mean than all the others, because all the others, we have some things in the middle there that kind of make the standard deviation a little bit smaller. I think A is a good distractor, but it's not right. Number two, ask what is the interquartile range of the ages here. So our IQR is the middle 50%. So that's our median, that's a 50%. There's an outlier out there. And so from 20 down to about, looks like 5 to me, or about 15 is the middle 50%, this box. That's not a choice, but 16 is, so it's 16. Let's see. Next one. Basically, they're asking you what's the shape of this distribution. And I think the hard part here, most of you probably know it's skewed, but I always have to remember if the tail is on the left, the outliers are on the left, that is skewed left. If the outliers or the tail is on the right, that is skewed right. Sometimes it's easy to get that backwards. So this is skewed to the left. I know these answers are right. I'm pretty sure they're right because I just did them and I've got a key over here if I forget. Let's see. Bank surveyed all 60 of its employees to determine the proportion who would participate in voluntary activities. Which of the following statements is true? So these are really hard where they ask where like one is true or one is false, and you have to just read through them. And in particular, pay attention to ones that look kind of close, because normally there's a word that's different. But after reading through this one, I found out that this is actually 4, because as soon as I saw it, I was like, they're doing a census, and I found down here it's a census. So there might be some others in there that kind of make sense, but they are doing a census with this. So that's why it's E. 5, once again, we got something skewed to the right here. Oh, I love this one because do not add all these up to try to figure out the median. Look in the problem. They tell you up there 175 patients. So I'm like, well, half of 175 is about 90. It's actually, I guess, 88, 87.5 maybe. But clearly, that first 80 doubled is 160. So it's got to be in this next block here somewhere. Because 80 plus another, 50 is 130. So the halfway point, the median point has got to be in that block there, which means the only thing between 5 and 10 is the 7.25. The next one, data were collected on the amount in dollars that individual customers spent on dinner in an Italian restaurant. The quartiles are below. So once again, there's our median, there's our interquartile. And if you read through these, they kind of don't make sense. It threw me off a little bit because the first one is right. At least half of the customers, wait, is that right? Hold on. Maybe misremembering this one. This is number 6, right? Yeah, at least half of the customers spent less than or equal to 44.27, and at least half spent greater. That's the middle number, and it's the first one, and it's basically describing what the median is. All these others are hooey. Okay, I really like this one because you can do it without a calculator. At least I did it without a calculator. You got a 500-pound bear, standard deviation of 50, 300-pound female bear, standard deviation of 40. What's the equivalent of a 530-pound male bear using the standardized score for female? So this is how I reasoned it out. I'm like, well, 550 would be one standard deviation higher than 500. 340 would be one standard deviation higher than 300. So I'm like, well, 530 is not quite half a standard deviation. So a little bit more than 20 added on 300, it's 320 something. There's only 2 good numbers here. The 324 and the 330 are the only 2 reasonable numbers. And I just kind of rolled the dice and said, it's got to be B. I could figure out the actual Z-score and do a lot of extra work for this, but I don't need to. All right, we got a distribution table. They tell you the expected value, which is basically the mean of all these things, and the standard deviation. And then they say, they create this equation, and essentially they're saying, I am taking my my distribution, and I'm multiplying it by some number, and I'm minusing some number from it. And there's two questions they can ask you here: is what happens to the mean, and what happens to the standard deviation? And the easy answer is the mean gets multiplied by this number and then shifted 100, whereas the standard deviation gets multiplied this number, but the shift doesn't do anything to it, because all the maximum and minimums will all shift by that 100. So that doesn't change the variability at all. The range will still remain the same. But when I multiply all the numbers by 75, everything kind of spreads out. So 75 times the 5.76, I believe that correct answer was, what's this, number 8? It's B, okay? And this gets a little dicey here too, because I think we get 3 B's in a row. Got a little scary. Let's see. Based on a survey of sample adults, 900. Oh, this one was a hard one. I'll just be honest. I actually have work on the back of my paper. This is one of the few times I actually pulled out the paper and started working. Let's see if you can see my work there. That's my work. Basically, I figured out the margin of error, and then the problem was when I unwound that equation, I got a Z-score of 1.65, which is easy to find. It came out as 95%, but then I was like, wait a second, this is a two-tailed test, essentially. Not a two-tailed test, but this thing has 2 tails on it. This thing has, if this is how big this thing is, I have 5% on both ends. That's what this is telling me, which means I have 90% in the middle. And I don't know if what I just explained makes sense. 95 is a great guess if you did all the algebra correctly, but then you have to realize that Z-score of 1.65 tells you how much you have left over on one end. And then you have to double that because you've got that amount left on both ends, and that you have 90% left in the middle. That might have been the hardest one, mathematically the hardest one in the group. So only one, like I said, that I kind of had to pull out some scratch paper. A lot of text here. There are a couple of things in here, but basically it seems like an experiment, and therefore it is reasonable to conclude that there is a difference of sales, and the question is caused by what? And it was caused by the cover designs, because it has nothing to do with sample size. I may not explain that one well, but that's what it is. Number 11, the manager of a swimming pool. Oh, this one I have a question mark by, because I wasn't sure if I was going to get it right or not. Randomized block design is typically, and I may get this wrong, I'm doing this off the top of my head, I only taught this 2 years, but randomized block design is when you have 2 things you're concerned about, and so you test both of them. And an example might be, I wanted to test all of my students how they did on a test, but I was also concerned that like the morning students might do better than the afternoon students. Then what I might do is put all the morning students in one experiment, both a control and a treatment group, and then all the afternoon students in another experiment, a control and a treatment group. So it's almost like I've got 2 experiments going on at once. But that's what randomized block design typically is. Definitely not matched pair, because matched pair is something else. I don't want to try to explain it in this context. But the answer here is, for number 11, it's a completely randomized design. This is not a block design, because we are not we're not concerned about 2 things. We're just testing the detergent A and B. That's all we're doing. We only have 1 washing machine. We're not randomizing the washing machines or anything like that. Let's see. This one I had to think about, because it said minimize response bias. And there's 2 sources of bias typically. One is that we underrepresent some groups. So randomly selecting helps, but that's really kind of with general bias. It's not about response bias. Response bias is typically like leading questions and things like that. So the answer here was E, but I wasn't sure I was going to get this one right. I was thinking maybe it's C. I'm not quite sure what the author of this question was getting at, but it is E. 42. This one also took me a while. Notice it's the rabbits in the sample, not in the population. Okay. This is a sample of 42 rabbits with a mean weight of 5. And I spent some time reading through this and realized, oh, wait a second, I got stuck on the 42. 5 is a pretty small number. 3 is a pretty big standard deviation. If I go 2 standard deviations to the left, I'm in negative territory, which is impossible, which means I must have a bunch of data out to the right of my 5 to make the standard deviation that high. So this thing is definitely skewed to the right, which I believe what the correct answer is, which is C. Okay. This is actually kind of a question once you wrap your mind around it. This one, very interesting. I think I know the right answer. They did not publish the right answer. They said they threw it out. I think the right answer is D, because I think if the null hypothesis is true, we are using the null hypothesis to calculate the standard deviation. So I think that answer is D. Maybe there's some wording in there that's misleading, which is why they threw it out. I'm not positive that's the right answer, but that seems like it's right to me. 15, once again, very wordy. I'm just going to tell you. So this irritated me a little bit. So they called random phone numbers. And I think when they said they did this, they're literally generating random phone numbers. I was assuming they were picking phone numbers from like a known list, as opposed to just every random number in the world. But evidently that's not what they're doing, because B is not, I think B is the answer actually. Let's see, what's 15? Yeah, B is the correct answer. Like, this is not a legitimate concern. And I'm like, I actually think that is a legitimate concern, but it's because they're randomly doing the phone numbers. At least I think that's why that's not a legitimate concern. It's like, we're just randomly calling numbers. Doesn't matter if your phone number's unlisted, we're going to randomly get you. So I didn't pick that one. I'll tell you, I picked, what's that again? 15. I picked D, because I couldn't quite figure out why people registered in, like, there are 2 people and why are those represented? I guess it means the second person in the household can never get picked. So that is a legitimate concern. And then I thought there was another good answer in here. There's a couple in here that you have to really think about. I'm going to move on. 16. Oh, this one you have to be kind of mathematically clever. So the chance of any one of these failures happening is this: if any one of them happens, we have a failure. So the question is, what's the probability of not having a failure? Well, the question is, well, me not having a failure is 99% and 97% and 96%. Each one of those independently can be multiplied together. So if you multiply 0.99 and 0.97 and 0.96 together, you get, I believe, 92%, because that's the chance of no failures happening at all. Because if one of them happens, the thing breaks down. But you had to kind of wrap your mind around that question. And I think this is one of those ones that if you see enough of them, you kind of know the trick. But if you haven't seen a lot of them, they're hard. Let's see. I got this one wrong just because I was stupid. I know it's got to be between 0.048 and 0.112. So B and C are the only 2 reasonable answers. And if you add those 2 together and divide by 2, you will get the correct answer, which is, what did I get? It's C, 0.8. But what I did is I subtracted 0.112 from 0.48, which gives you and divided by 2, that gives you the margin of error, which is 0.032. I was so happy I got the right answer. I realized I wasn't done with that number, because I needed to add it on to the 0.048 and get this. That would have gotten me that. But I stopped halfway through. Maybe in a real exam, if I had extra time, I would have caught that. But I didn't even, so happy the right number came out of my calculator. I did not even bother to reread the question and think about the context. So I made a mistake. Let's see. One sample T procedure. The reason we do this, I was not sure when I was going to get this one right either. Because I generally think the reason we do that is because we want to be able to use the standard deviation. The problem with this wording is sample standard deviation is a good approximation for the population standard deviation. That's not quite right. And this whole being a sample size of at least 10, what it does is, or 10 times, sorry, at least 10 times the size. When we're sampling without replacement, every time we take something out, it changes the odds of the next thing that comes out of the hat or out of the sample. But if our sample size is really large, the difference between that conditional probability and just putting it back in and resetting all your odds is pretty small. And so that's where the degree of dependence among observations is negligible. Each time I observe something, I am changing the odds a little bit, but not so much that it's going to mess up my standard deviation. It is related to the standard deviation formula, but this wording is just not quite correct. So if you pick C, it's a pretty good distractor. D was the correct answer. I didn't even think about A, B, and E. All right. This distractor almost got me because I was thinking 95%, and that's probably right if like you get a 95% chance of winning or something, or 95% chance of losing. But this is basically, I mean, your chances of losing are pretty big. You $1 each, 1,000 tickets, only one person wins, $50. That is not very good odds, not a very good lottery. It's for charity. So basically what that negative 0.95 means is like everybody who buys a ticket is expected to lose 95 cents. Somebody's going to win, but if we average it all out, all the losers of $950 averaged out with the one winner of $50. On average, everybody's lost 95 cents on average. Most people have lost $1, but that one person won 50. And finally, number 20, we're doing a hypothesis test. We want the alternative. The alternative is mu is less than 10. Assume this is true for a fixed sample size and significance level alpha, the power of the test. All right, so what the power of the test is, remember, if you've done it, the power is given some number, how likely are you to reject the mean in favor of the alternative? You've got to have an alternative for a power to even make sense. So the further that mean that's not the null is from the null, the more likely you are to pick the alternative, and the more powerful the test is going to be. And there's a really good picture that I show in my class about this. But basically the idea is you want whatever your mean is, it's probably 10. You want this to be as far as away in the correct direction. So if you pick 13, you were thinking the right thing, but you went in the wrong direction. So if the true mean is 8, I am more likely to reject the null and pick the alternative than I am if it's 9. Because 9 is lower, but it's close enough to 10 that occasionally I'm going to accidentally not reject the null, fail to reject the null. Okay, that's the first 20. I may do the second 20 someday, but I just finished it myself. And rather than explain it to everybody individually in class, I just thought I'd do a quick video. So let me try to stop. There we go. Stop sharing and bye-bye.